morning, everybody. Hope you're not suffering from much jet lag as I am.
Excuse me, do you want a warning at 10 minutes or 5 minutes?
5 minutes.
5 minutes.
I'll try and keep my eye on the clock,
Okay.
just in case. Sometimes I get wrapped up in this. Okay, the title is the tie that binds the fundamental unit of change in space and time. Now, I'm asking a basic question. Why, despite all facts to the contrary, all efforts to the contrary, have attempts at unification between quantum and relativity been unsuccessful? Until 55, Einstein was working on unification from a general relativistic point of view, and since then it's been all the particle theorists and supergravity and all the unifications from particle theory and the quantum. But they've never been able to do it. I contend that that's because we don't understand what the quantum is. We know all the mathematics and everything about the quantum. We don't know what the quantum itself is. We know it mathematically, we don't know it philosophically, so that's making it hard to unify them. So only with a true understanding of the physical nature of the quantum will the unification of the quantum and relativity ever become a reality. These 3 pages are just the abstract that they had. Okay, now many scientists have admitted over the years that they know nothing, or they know everything about the quantum, but they have no idea what the quantum is. In fact, the physical origin of the quantum is just totally unknown. It's very common for all the top scientists to say, well, we know everything, but we don't know what it is. In Physics Today magazine, in the Physics Forum section last month, well, I was writing this, it came out, so I thought I'd include it. A physicist by the name of M. David Merman stated, quantum mechanics is the most useful and powerful theory physicists have ever devised. No one's going to doubt that. Yet today, nearly 90 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year, none ever disappear.
Go to the side of it. Yeah.
Can you see it now? I contend this misunderstanding is actually a product of the physical interpretation of the mathematics involved. Merman says in his letter that people don't understand probability theory. And I say, no, people don't understand the physics. I'm a physicist. Probability theory is just mathematics. They don't understand the physics of interpreting the probability to the physical situation. That's because during the late 18th and 19th centuries, mathematics was rigorized by purging mathematics of all references and connections to physical origins. Math originated in physical space.
No, not that way. It's on the chord. Let's move it the other way.
No, the chord is okay.
It's okay.
You know what I mean? Let's move it way over so you're not standing in front of the screen.
Then I've got to move over here. Sorry. Now, mathematics was purged of all references to the physical world during the 18th century. This is called rigorization. And then it became extremely abstract, so it no longer matches physical reality in many cases. So we take that mathematics back and try and apply it to physics. They don't find a match, so they make something up. It's all part of the process. Now, the concept of non-commuting variable pairs, or variables and variable pairs, that is used in quantum theory is wholly a mathematical abstraction and does not exactly have a physical meaning, a physical counterpart, no real world counterpart. Now the individual quantities, the uncertainties in momentum and such, they do have physical counterparts, and we can measure them, of course, but there's no physical connection between the two. I'll go on to show that. Yet the physical quantities represented by the Heisenberg uncertainty that are interpreted probabilistically are only connected by their non-commutability. Understanding this fact is the key to understanding the main problems of the quantum theory. More recently, there's another recent article, Tom Siegfried has written that these same fundamental questions that concern Einstein and Schrödinger continue to disturb many physicists today. What quantum mechanics really means, where it ultimately comes from, why it denies the cause and effect certainty of traditional physics are questions that haunt the deepest of scientific thinkers and divide them almost as badly as 21st century political parties. I like that part. Physicists simply can't agree on how to interpret quantum physics. They fight like cats and dogs over it. And of course that brings into mind Schrödinger and Einstein versus Bohr and Heisenberg on the question. In the end, at the heart of these disputes is the very nature of reality itself, and whether quantum physics is the last word on how to describe it. Now basically I approach unlike 99% of physicists working on a problem, I approach unification from the relativity side. I'm an Einsteinian. I don't approach it from the quantum side. These problems render the present use of quantum mechanics as the basis for a majority of physicists' conceptions of physical reality questionable, my words, questionable and in need of closer scrutiny. Unfortunately, the unification can never be accomplished, my thoughts, in spite of all efforts to do so until these issues are resolved or otherwise eliminated. All unification schemes, unification schemes, theories and models, whatever we want to call them, they're doomed to failure until the true physical meaning of the quantum is discovered. And that's what the rest of my paper is about. Now, as presented by the Heisenberg uncertainty principle, quantum theory is pure and simple example of mathematics that has been dissociated from the real physical world, coming back to haunt physicists, who are unable to properly interpret the mathematics. Now, quantum mechanics is based on the commuting pairs. The uncertainty in position times the uncertainty in momentum is greater than or equal to h over 4 pi, and the uncertainty in energy times the uncertainty in time is greater than or equal to h over 4 pi. Now, and therein lie hidden variables. There's a lot of talk about hidden variables. People say that Einstein was the first one to bring up hidden variables in 35 in EPR. That is absolutely not true. There's nothing about hidden variables there. They came along later with de Broglie and Vigier. Their hidden variables were developed in 51, I think it was. But these hidden variables are so simplistic, they've gone completely unnoticed. Get ready for the surprise. The hidden variable in the equation, delta x, delta p greater than or equal to h over 4 pi is time. There's no time in that, duration. A hidden variable in the uncertainty in energy times time, uncertainty time, is space. So it's missing out. The first equation here is time, and the space is missing here. Those are hidden variables. Now that is for a reason. The reason is that delta E is space-like, but it's not space. Energy is a fundamental quantity, can't be broken down to a position. And delta P, the momentum in the first equation, is a fundamental quantity. Momentum is a fundamental quantity, even though we classically treat it as m times v over t. That's not what it is in quantum. It's just momentum. So they can't be broken down into more fundamental quantities. So these equations and their mathematical products do not fit the space-time continuum as expressed in relativity theory. I can fix that. Just bring space and time back together into a single uncertainty equation. And you bring space and time back together so they can be used. Just set these two equations equal to each other. They're both equal or greater than h over 4 pi, so they're equal to each other mathematically. From that simple algebraic setup, I'm not going to do it here. Notice Planck's constant disappears, as does the overly restricted relationship between non-commuting conjugates, because we have commuting conjugates now in the same equation, demonstrating that the uncertainties are inherent in the mathematical abstraction of the uncertainty principle rather than nature itself. So there's no uncertainty in nature. This yields two possibilities. I take the ratio, the uncertainty of position over the uncertainty time. I say less than or equal to c. I am not saying that that ratio is speed. It's not speed. It's a ratio of two numbers. But as a ratio of two numbers, I can still say it's less than or equal to c, because c is also a physical constant, as in E equals mc squared. Doesn't mean that something's traveling the speed of light. Doesn't necessarily mean that. Or the ratio of delta x over delta t could be greater than c. I call this ratio the Einstein certainty condition, and I call this ratio the Heisenberg uncertainty condition. Using Einstein certainty ratio, I can actually, through simple algebra, I can derive, just on how you define your delta x and your delta t, how you define those, you can derive time dilation, Lorentz-Fitzgerald contraction, and the E equals mc squared, actually mc squared plus m0 c squared. You can derive those equations just on how you define delta x, delta t, and delta e and delta p in the relationship I gave. all by simple algebraic manipulations. I tried to publish that paper in '92 on doing those derivations. And what I've said so far, I've tried to publish in 1992. First, I went to Foundations of Physics. It was rejected immediately within a week because it was too philosophical. It was recommended I send it to a Philosophy of Science journal. I sent it to the British Journal of Philosophy of Science. They took about 6 months and rejected it because they said it's not timely, nobody's interested in this question anymore. And so then I put some recent references and sent it to Philosophy of Science, the Journal of the Philosophy of Science organization in the United States. And they rejected it about 7 or 8 months later, no comment. As my peer reviewers didn't even make any comments on it, they just rejected the paper. Now, I can also derive, I get rid of the uncertainty relationship, or the Einstein uncertainty relationship, delta x over delta t is greater than or equal to c. I can also derive Newton's second law, simple algebra. It only takes about 4 steps. See, putting these together, getting rid of h, I can derive all of classical physics. And what I've done by doing that is I put space and time back together, so I'm back in the space-time continuum. So we get both relativistic physics and Newtonian physics back as space and time are reunited from their unnatural, non-commuting separation by the Heisenberg uncertainty principle. Now this demonstrates that time and space are hidden variables in the uncertainty relationships. But they also demonstrate that Planck's constant is the binding constant of space and time. So Planck's constant, h, is actually a binding constant. That's its purpose in physics. Now, to reevaluate quantum and discover its true physical meaning, we need only look at a simple space-time diagram. First, we identify Einstein's certainty and Heisenberg uncertainty on the space-time diagram. Simple, here's your light cone. The quantum event is at the origin. So this is the light cone for any given quantum event. Inside the cone, you have the ratio delta x over delta p is less than or equal c. Then you have the speed of light. And what Minkowski called the absolute elsewhere out here, what lies outside the light cone of any given event, is just the absolute elsewhere. And of course, that's where entanglement takes place. So this gives me a way to actually define what entanglement is, but I'm not going to do that here. Next, we look more closely at the origin diagram that defines an event, a quantum event, at a dimensionless point. Quantum physics refers to dimensionless points. And of course, that point where space-time together is a dimensionless point. Now what we're going to do is we're going to literally squeeze a measured distance in space down to a point, the event, at the origin of the space-time axes. By doing so, we approach the uncertainty limit on measurement in both space and time. Remember, this is a dimensionless point at the origin, so we're just squeezing down, approaching it. We collapse. This is tantamount to collapsing the wave function. This gives a visualization of the smallest unit of measure possible, literally the quantum. I'm defining the quantum now, not Planck's constant, I already did that. This is the quantum. Now the quantum is a sphere of probability surrounding the quantum point event. On this diagram. So this sort of squishes it, that's actually round. You've got delta x, more or less a sphere in space-time, an imaginary abstract sphere, not a real one, around the point event, dimensionless point event, you've got delta x and delta t. Now, inside, you've got Newtonian absolute time and absolute space because Newton related those to a point in space. So essentially, you've got Newtonian physics here. The lines, the axes are actually relative 3D space, relative time. So a quantum event is a dimensionless point at the origin, as I said. But this circle of uncertainty around it is the basic unit of change, in the old Greek sense of the word. It's the unit of change. And then Planck's constant would be what ties it together at that point, or within the sphere. Think of this as a sphere of fuzziness, probability, as a depiction of an infinitely dimensioned Hilbert space, with each point in space and time defined by its own little 4D space-time axis. I remember learning that in graduate school. We had quantum physics back in the 70s, early 70s. Each point, 4D axis, space-time axis, would be spinning around probabilistically within the sphere until the wave function is collapsed. So within, you have some random quantum event. It's not a probability like they interpret in Heisenberg uncertainty principle. It's not a probability spread out over space and time. It's that little 4D space-time of the event. And it's just more or less, bouncing around or swerving around inside there. Now when you collapse the wave function, what that does is the time axis, probability time axis, has to align with external time because there are other events in the universe. So it has to line up with time on the other. And when the time of the event, probabilistic time inside that unit of change, lines up with the rest of the universe, it's collapsed wave function, and the process becomes real. The event becomes real when its time axis aligns with the time axis of the outside world, all the events together in the outside world, because time continues passing relative to all objects in the universe outside, external to the probability sphere. I'm not talking about absolute time. It's not absolute time, because all the different events outside relativistically determine the time axis. The probability sphere representing the quantum unit of measure. Now, the mathematical abstraction of collapsing wave packet, it occurs only within the sphere, not the universe at large. As I said, these are Hilbert spaces. By forcing the time axis and thus the space axis to align with the external space-time continuum. The universe or nature is neither deterministic nor indeterministic. That's all in our heads. It has nothing to do with nature. Determinism and indeterminism. These concepts have been argued about so much, but they are completely irrelevant to physics. They're our mental abstractions. They're not in nature. It's not even a question. The terms don't even apply to nature. Nature is. No more than that. Nature is. Classically, the problem has been seen as an inability to unify the discrete and continuous nature of physical reality. But these distinctions only mask the real significance of defining quantum within the context of relativity. The determinism and indeterminism argument is just an obfuscation of what we should be doing in physics. The real difference that needs to be addressed is the difference between a point-based or discrete geometry and an extension-based or continuous and metric geometry. They don't match each other. You have two geometries. You have extension geometry, metrics, and you have point geometries. They're slightly different. The same problem between point and extension-based geometries was a sticking point in Einstein's and other people's attempts to unify gravity theory and electromagnetism. The Russians have done a lot of work in torsion theory. This actually, I'm not going to use the word, but this actually refers to torsion theory. I call it something else. I call it twist after Clifford. This problem represents an ageless debate that has been addressed over and over again in history, from the origins of calculus and Euclidean geometry to Riemann's generalization of differential geometry. You have either one of two cases in all of our physics. The defining condition for calculus, the limit is del t goes 0, del x or del t. These aren't probabilities. They are, of course, differences. Or ds is equal to square root of dx squared, which defines metric in a simple metric in Riemannian generalized differential geometry. But 0, in both these cases, we're either approaching 0, never reach it. In other words, we never reach that dimensionless point. In this case, we're shrinking down both sides, so we get smaller and smaller line elements or volume elements or space elements. But 0 is only approached. And so 0 is only an approximation dose. On the other hand, every extension in geometry, going all the way back to Euclid, is made of an infinite number of dimensionless points. This fact is demonstrated by numerous continuity theorems in calculus. But we can't duplicate those in extension geometry. That's the whole thing. So this dates back to Euclid. If we can abstractly squeeze geometric and algebraic extensions down to a limit of dimensionless points, it seems that we should be able to build that same extension out of dimensionless points. In other words, you take dimensionless points, put them together, we should get a line. As far as I know, some of you know better in mathematics than I am, and that's not very hard to be. Has anyone ever taken points and built a line out of it? A theorem or something? I don't know of it. So I've done it. This process is actually implied in Riemann's original development in the 1850s of a differential or metric geometry of spaces in the notion that every real n-dimensional space is embedded in an n+1 dimensional space. So Riemann was implying this in his habilitation shift lecture in 1854 when he did his generalized geometry. Yet I know no one has done this. Now I call this theorem that I'm proposing a reality theorem for three-dimensional space because it gives the conditions for reality, physical reality. This is literally my title, the tie that binds. The problem in doing so, how can two dimensionless points be linked if they are dimensionless? If you take two dimensionless points, they have to be contiguous or touching before they can form a continuous surface. But if they're dimensionless and touching, they're coincident. How the heck do you do that? That's the sticking point. The solution to this problem, first of all, apply Gödel's theorem, but you also have to apply a proper definition, a mathematical definition of contiguity of dimensionless points. The second one is the real sticking problem. The Gödel's theorem is the way to get around that. Gödel's theorem, a mathematical theorem will establish a system. That system can only, the consistency of that system can be proven within the confines of the theorem, but the theorem can't be proven. You have to go to a more general theorem to prove the original theorem. It's a truth test. This means that the existence of a physical 3D space can only be proven mathematically by utilizing the geometry of an embedding four-dimensional space. This is what Riemann was implying. Two-dimensionless points, this is my definition for contiguous points to form a continent. Two-dimensionless points are contiguous and then form a continuous extension if and only if another dimensionless point can be inserted between them. Now, simplest space, one-dimensional space. This is one in 3 dimensions. This is our fourth embedding dimension. These are 2 points. These are 2 contiguous points. We extend them into the fourth dimension. That extension. Now we can't use. We're trying to use A and B to define the continuity in 3-dimensional space, but I can state that they must be continuous in the higher dimension. Now, if that's a straight line, Euclidean flat space, I haven't done anything because no matter how I go, no matter where I go into the higher dimension, they're still not touching. Now I define this by saying I can put another dimensionless point in there. So they must be contiguous because there's not enough room to put another dimensionless space point in there. They don't meet the higher dimension, so that's no good. How do we get around this? We curve the line. We have a curved space. When we curve the space, these 2 points will come together up there. That's a single pole. That is a single, this is a single polar Riemannian embedding space. They must come together. They can be coincident in the higher dimension. They can't be coincident here. But this proves that they must be coincident here. Because if you look at, if you go from the single pole up there down to 3-dimensional space, they separate with nothing between them, so they must be contiguous. Therefore, doing continuity on the space. Then you put other points on either side of them, and you build up your 3-dimensional space, 1, 2, or 3-dimensional space. Now, this gives us 4 strict mathematical requirements placed on the higher dimensional embedding space to guarantee the reality of our 3-dimensional space. Now, these mathematical restrictions define our 3-dimensional space. First, a 1-dimensional line extending in the 4th direction from the dimensionless point in 3-dimensional space must complete a circuit and return to the same point from the opposite direction. And 2, all lines extending from all dimensionless points in 3-dimensional space must be of equal length. Does anybody here recognize those conditions? They're actually quite famous. Superstring people don't know them, but they are famous. Those are conditions Kaluza put on his unification of electromagnetism and relativity in 1921. Exact same conditions. Those are mathematical restrictions. And then later those were used by Klein, 1926, 27, those were used by Klein, saying that that loop in the higher embedding space was equal to a factor of the quantum. And that's where you get Kaluza-Klein geometry. I already said that. The other conditions are that the 1-dimensional lines extending into the higher dimensions from 3-dimensional space must be at least as long as the circumference line that completely encircles the embedded 3-dimensional space. So that higher dimension must be as big as 3-dimensional space in any given dimension. All of the 1-dimensional lines that extend from the dimensionless points in 3-dimensional space must pass through a single common point, the pole, in their circuit before returning to the 3-dimensional space in the opposite direction. Now, the only way you can go through a pole is if you have a twist. It's a Möbius strip one-dimensional Möbius strip going around. So everything switches over. That is a half twist. This geometry originated with William Kingdon Clifford in the 1870s when he was trying to explain Maxwell's electromagnetic theory. He used this to explain electromagnetic induction. The last two conditions can only be fulfilled then if the higher embedding space is macroscopically sized, just as Einstein and his colleagues proved in the 1930s. Einstein, as far as I can tell, didn't know anything about Clifford or Clifford geometries and such. But Einstein, Bergman in 38, Einstein, Bergman, and Bargmann in 41 tried to develop a five-dimensional space-time geometry based on Kaluza's theory by extending, instead of having the submicroscopic loops, as the superstring people do in Klein theory, Kaluza-Klein. He cut out Klein, went to original Kaluza theory, and tried to develop a unification. They were unsuccessful, so Einstein gave it up. He gave it up, as he later stated, the second appendix to his Meaning of Relativity that was published in '56 after he died. He cited three different possibilities for unification of physics besides his own attempt. And one of them was the Kaluza theory, going to a higher dimension. But he said, if we cannot understand why we don't sense that higher dimension, we can't do it. Why we don't sense or detect it. So he gave up the five-dimensional theories, even though he was enthusiastic about them all the way to his death. Now this means at each point with my theorem, this means that each point in three-dimensional space would have to have a half twist to it. In other words, these conditions determine what is real, i.e. particles, in three-dimensional space. So I'm saying that all real particles must have half spin. It is called twist by Clifford. I'm not going to call it torsion, but it is related to the torsion theories. It is twist because that's what Clifford originally, and it all originated with Clifford. Cartan geometry used in 29 for unification by Einstein that a lot of the torsion people refer to. Cartan's geometry was based on Clifford's previous geometry of twists. So it all goes back to Clifford. Yay, England. He taught right up the street here. They also rule out the possibility of theories that depend on infinitesimally small or compacted higher dimensions could not possibly represent, I left a not out there, could not possibly represent physical reality unless those theories can account for the physical effects that adopting higher dimensions have on three-dimensional space. You can't just say the dimension is this, the dimension is that. You have to state geometrically how those affect your three-dimensional space. You just can't say they're there. Consequences. All real material particles must have one-half spin. That limits real particles to proton, neutron, which is a composite, electrons, muon and tauon, and neutrinos. They're the only real particles. All the rest are just energy, resonance, temporary states going between real particles and high-energy experiments. And all higher dimensions must be as large as all three-dimensional space. Goodbye standard model, and goodbye superstring theory, hello unification. Thank you.
Thank you very much for that, Jim. Any questions? So Albrecht first, and then Guy and Miles.
A comment you have said, and I agree to this from my full heart, that a quantum theory is a mathematical model which has decomposed from physics. But the same, I think, is true for Einstein's relativity. That is also a pure mathematical model which is decomposed from physics. You can see it at one fine example. Einstein has made, when Einstein makes comments or statements about the space, that the space is contracted or curved, this is pure mathematical because there is no physical means to test such a statement. We cannot measure space. There's no way to do it. So what we say about space is mathematics, and we hope that we can use the results, like in quantum mechanics, we use the results, but it's not mathematics. That is a bad thing. So I disagree that this can help us.
If you go with just the first two rules I gave, which is what Kaluza does, you get the intrinsic space that Einstein ultimately adopted. He is too positivistic. But if you go to the other two, that imply the conditions on our three-dimensional space, i.e. that all real particles have spin. This space, the three-dimensional space I've built from this, also has other certain characteristics. It allows for rotation and linear translations. And it gives you your basic symmetries, mirrors of symmetry, rotational symmetry, translational symmetry. And those are conditions of space. I don't think any other geometrical model actually can state explicitly these conditions. These conditions are our universe. So it is implied. That is a real model. Now, if you go to an extrinsic curvature, five-dimensional space-time, then the curvature becomes real. Then you have to ask what the field is. The field is a single field. What Einstein called a unified field, I call a single field. And then all of matter, space curvature, anything, are just condensations from that single field. If you want to call it ether, yeah, go ahead, I don't care. But that's what it is.
Go.
I agree with you.
Very quickly, Jim, you seem to be saying that real particles exist in 5D.
No, they're three-dimensional.
Okay, they're three-dimensional.
Yes,
but they're
curved in
extended
a higher dimension.
Right, but Kaluza's 5-dimension, surely.
Yes.
Right. Could it not be that we only have one of those or two of those dimensions in our 3D world, and the others of the four are in time or extended one dimension in time? Is that another way of looking at it? Why go to 5?
I am stating that the fifth dimension, the extra dimension, is more space-like than time-like. But our three-dimensional space is not connected to time. I said the quantum or Planck's constant is binding constant for space-time. It connects four-dimensional space to time. Our three-dimensional space is a subset of the four-dimensional space.
But what we live in 3D might only be two-dimensional.
I know other people have that theory.
You need time.
To answer you, in a sense, light fits that requirement.
Right.
That's why light is different from matter.
Talk to you later.
Miles.
Have you any reason for thinking that Planck's constant is an absolute constant of physics? I don't believe that there's any such thing.
I don't know that it is. I don't know the gravitational constant. I have implications gravitational constant might vary also.
I think it's merely a convenience to treat it as that.
Yeah, I believe that too. The constants may vary. In fact, the speed of light is only in our three-dimensional, I call it a sheet. It's only in the three-dimensional sheet. The speed of light varies as you go into the higher dimensional space.
Do we have any further questions for the speaker?
So how many constants do you accept in your work?
Well, I have it in the paper. I didn't put it in the talk. There's more in the paper. I didn't put it in the talk.
12 or less?
There are basic, as far as I'm concerned, there are three basic constants. There are probably more, but there are three basic. Speed of light is not a basic constant. Permittivity and permeability is constants. So if you vary either, speed of light is not constant. It varies in water. Why? Because permeability and permittivity. So permeability and permittivity are the things that bind space together. Electrical permittivity binds three-dimensional space together. Permeability, magnetic permeability connects three-dimensional space to four-dimensional space, and then Planck's constant connects four-dimensional space at a time. In my model, my overall model.
Well, sorry, I would like to contradict. Permeability, as you call it, this is a constant, correct? Yeah. But permeability, the magnetic part, is not a constant because magnetism is not a primary force. Magnetism, as we know, a relativistic side effect.
In normal physics, I'm changing normal physics. I also work with 8 laws of thermodynamics instead of 4, but that's another talk.
Yeah, but Maxwell, in his mathematical model, has presented us a very beautiful mathematical way to calculate electrodynamics. But it has a symmetry of electric and magnetic effects. But this symmetry is not physical. In physics, we only have electric charges, not magnetic charges, by good reasons. The magnetism is a relativistic side effect. And in the moment when speed of light would be infinite, we would have no magnetism. That is a logical connection, not the other way around. So, the magnetic permeability is a consequence of the speed of light, and not the speed of light a consequence of permeability. Okay. That is logically exchanged.
May I ask you a question? Do you know what a vector is? A vector has magnitude and direction, right? In mathematics. Where's the magnetic vector potential?
That is the side effect I call it.
No, it's not a side effect. It's a side effect in three-dimensional space because that is a vector in the fourth direction
That's a very, very simple side effect. Do you know the lens-tilling effect?
I am saying Maxwell's theory is incomplete. It is not complete. In the 1870s, Clifford tried developing a four-dimensional space to explain magnetic induction, and he implies that magnetic vector potential is a twist in the higher dimension.
Twist is also something which is mathematical.
No, it is not. I'm saying it is real in the higher dimension. And that's because using it gives me the conditions for three-dimensional space that have already been shown to be correct. Well, I didn't include that in this talk. This talk is not about that. That's my general theory. This is just a philosophical basis on the quantum to give me my general theory.
Okay. Any further questions? Okay. Well, thank you very much, Jim, especially for sticking to time, which has given us leeway. I think what we will do is start the next talk immediately.